In this video, we are going to learn how to use matrices to solve systems of equations. So you might be thinking, what is a matrix? Well, a matrix is just a rectangular array of numbers arranged in columns and rows. And whenever you have seen like tables of data, that's really a matrix. Or if you use Excel, that's also, you can think of that as a big matrix. So you've used matrices before. Matrices can be of different sizes, and so this matrix that I have shown here has two rows, and it has 3 columns. First column, second column, third column, so this is a 2 by 3 matrix. We can have a 3 by 4, we can have a 5 by 2, there's matrices of all different sizes. How is this going to help us solve systems of equations? We already have 2 fairly good methods for solving systems of equations, substitution and elimination, but the issue is that with these methods, they work really well when we have 2 equations and 2 unknowns. But if we have more variables or more equations, these methods get really tedious and complicated and aren't a great way to do it. This method that we're going to learn is an algorithmic way, a step-by-step way that allows us to cut down on the work and make it more systematic. The first step in finding or trying to solve a system of equations using a matrix is to write what we call the augmented matrix. So when we're doing this, we're going to take each of our equations and we're going to turn it into a row in our matrix. Notice that we have 3 equations here and we have 3 rows in our matrix. Also notice that we have 3 different variables and we have that right hand side, which I'm going to abbreviate by RHS, and so 3 variables plus the right hand side, that's going to make 4 columns. So the right hand side, oftentimes we have a line drawn right there, but I can't get that to draw on my software that I use to make matrices. Each row or each equation is going to make a row in our matrix. So if we look at our first equation here, the part that we're putting in our matrix, we're not putting the x, y, or z. What we're putting is the coefficients of our variables and our right-hand side. This first column is the x variable coefficients. The second column is the y coefficients. The third column is the z coefficients. And the last column is our right-hand side. If we look at our second row, so I have 2, 3, 5, 8, and that's the same exact numbers I have in my matrix. On this last equation, we have 4, but we don't have any y, so we could think of it as 0y plus 5z equals 2, so I've got 4, 0, 5, 2. What we're going to be doing is we're going to be taking our augmented matrix that's got the coefficients and then we've got the right-hand side, and we're going to be putting it in what's called reduced row echelon form, which we're going to abbreviate as RREF. So we're going to find the RREF matrix for our augmented matrix. Here is the RREF matrix for that particular system of equations, and I want you to notice a couple of things. So first of all, along this diagonal here, we have 1s, and then above and below those 1s are a bunch of 0s. And then we still have the right-hand side with other numbers. The reason why this is helpful is because if we take this matrix, this RREF matrix, and I put it back into equation form, this first row, if I put it back in equation form, is going to look like 1x plus 0y plus 0z equals 3, so it tells me x equals 3. My second row tells me 0x plus 1y plus 0z equals 4, so it tells me y equals 4. And then the last row, it tells me 0x plus 0y plus 1z equals -2. So I get z equals -2. What I know is the solution to my system of equation is the ordered triple 3, 4, -2. Let's do a couple more where we write down the solution to our system. So we're going to assume that we have variables x, y, and z. And remember, this is like my x column, this is my y column, this is my z column, and this is my right-hand side. And I'm going to take each row and write it in terms of the equation so I can report the solution. So this first row tells me 1x, so it's just x, plus 0y plus 0z equals 3, so my x value is 3. My second row tells me 0x plus 1y plus 0z equals 4, so y is 4. And then my last row tells me 0x plus 0y plus 1z equals 1, so z equals 1. So my solution to this system is 3, 4, 1. So you try this next one. Did you get -305? Good. When we were solving systems of equations where we had two unknowns using elimination or substitution, there were three scenarios that happened. Either we had two equations where when you graphed them, they intersected at one spot. That was a scenario where we had one solution. And these were always the easiest to do because it just worked out. You went through the process and you got x equals, say -1 and y equals 2. So you knew what your values were. Another thing that could happen is we could have two lines that never intersected. And when this happened, we ended up with no solution. And what we would see was we would see a false statement, like 0 equals 1. And the same thing's going to happen with the RREF matrix. The final thing that could happen was you ended up with one line, even though you had two equations. The two equations were really the same equation. They just looked different. And we recognize this because we ended up with a true statement like 0 equals 0 or 3 equals 3, and we were able to solve for one variable in terms of the other. Again, it's going to work the same exact way when we're dealing with the matrices. To determine what type of solution a system of equations has, what you're going to do is you're going to go and translate your RREF matrix back into equation form. Let's look at an example. So notice here I have a matrix that's got 3 rows. That means I have 3 equations, and they tell me my variables are x, y, and z. So this is my x, this is my y, this is my z, that's my right-hand side. And where we're going to look first when we don't have the ones along the diagonal, we're going to look at that bottom row. So if I translate that back into equation form, I have 0x plus 0y plus 0z equals 1, so that tells me 0 equals 1. That's not true. That's a false statement. This means there is no solution to this system of equations. There's no x, y, and z value that solves all three equations. Let's look at another one. So here I can tell I've got 3 equations, but I only have 2 variables. I've got x and y, and then this is my right-hand side. I don't have ones along all the diagonal. I have the row of zeros, so this doesn't give me a false statement. This gives me 0x plus 0y equals 0. That's okay. And you might think that, oh, this must have infinitely many solutions, but it actually doesn't. If you translate this back into equations, this looks like x equals -3, and the second equation looks like y equals 2. So we know our x and y values, and our solution is the point negative 3, 2, we just got this weird row of zeros because we had one more equation than we actually needed. If I have two variables, I'll need two equations to come up with a unique solution. Let's look at another one. So again, we don't have the ones along the diagonal. We have this 0 here that kind of screws that up. That bottom row, if I translate it back into equations, or an equation, it looks like 0 equals 0. That's a true statement. Let's take our two rows though and translate them into corresponding equations. So the first row tells me x minus 2z is 4. The second row tells me y plus 3z equals 0. What we've got here is I've got x, a formula with x and z, and a formula with y and z, and what I can do is I can solve both of those equations for x and for y. So the first one would look like x equals 4 plus 2z. All I did was I added 2z to both sides. And then the second one looks like y equals negative 3z. So I subtracted 3z from both sides. And so I could say that my solution to my system of equations is going to be points that are of the form 4 plus 2z, negative 3z, and then just z. Any point, any x, y, and z value that solves all three of our equations has to have this form. And we could choose different values for z and then come up with different values for x and y. So we have infinitely many solutions here. There's many possibilities. Last example. First of all, I have two equations and I have three variables. Two equations because I've got two rows, three variables because I have four columns. I know that I don't have ones all along that diagonal because I'm missing a row in order to get a unique solution. But let's go ahead and do the same thing that we always do. Take our matrix and put it back into equation form. The first row tells me 1x plus 0y plus 0z equals 3. And my second equation, my second row tells me y minus z is 4. So that we could solve this for y. Y is 4 plus z. Here's another situation where we're going to have infinitely many possibilities. My x coordinates are always going to be 3. My y coordinates are going to follow this pattern. They're going to be 4 more than our z value. So once again, we have infinitely many possibilities. Hope you found this video helpful.